In this video, we are going to look at the physical properties and acidity of carboxylic acids. All right, so carboxylic acids, if you look at them, you'll see, of course, that they have a couple of groups that we're very familiar with, the C double bond O and the OH. All right, we know that the C double bond O is an excellent hydrogen bond acceptor, but not a hydrogen bond donor, and that the OH group can be both. All right, we also have an important resonance stabilization of the carbonyl group by this oxygen lone pair. Let me just draw it like that. Sorry, this drawing's getting a little bit messy, but this stabilizing of the carbonyl group by the oxygen lone pair tends to make the C double bond O less reactive to nucleophiles than the C double bond O of aldehydes and ketones. All right, because of this hydrogen bonding situation, sometimes people write this dimeric structure here to explain the unusually high boiling points of carboxylic acids. All right, in addition to the hydrogen bonding, they have strong dipole-dipole moments from the carbon-oxygen bonds, and they have van der Waals interactions, much weaker though from the R groups. Okay? All right, so we've used in the past boiling point as our major way to determine attractive or intermolecular forces, and what we see here is that the carboxylic acid has a much higher boiling point, about 165 degrees C, relative to a ketone with the same molecular weight, relative to an alcohol with the same molecular weight. Okay, so this is has strong hydrogen bonding, and this has strong dipole-dipole attractions. All right, water solubility, we see a similar effect. The carboxylic acid group has much higher water solubility than either the ketone or the alcohol that we're comparing it with. All right, okay, so when we look at structure of a carboxylic acid, we of course have a hydrophobic part and a hydrophilic part. And the water solubility is determined by the relative sizes of the two. As long as there's no more than about 6 carbons per COH group, we have a fairly water-soluble compound. That's a relative term. We tend to take 5 grams per liter as the dividing line between insoluble and soluble, but obviously it's just a continuum, but it becomes less soluble as the hydrophobic part gets bigger. All right. Acidity is the most important physical property of a carboxylic acid. For a long time, we've been using acetic acid as a reference compound for the acidity of other functional groups. And you may remember that its pKa is just a little bit below 5 right there. Okay, remember something about pKa's. The lower the pKa, the stronger the acid. Okay, all right, as we take the hydrogens here and replace them with more electronegative groups like chlorines, for example, what we see is the acidity increases. With one chlorine, it's the acidity is now 2.86. It becomes even more acidic when you put 2 chlorines like you have here, and when you have 3 chlorines, it's actually becoming a strong acid, even by the definition of strong acids we used in general chemistry, right? So it's a very acidic compound. Okay, so fluorine is more electronegative than chlorine, and what we see here is that the analogous trifluoroacetic acid is even more acidic than trichloroacetic acetic acid, right? The pKa of trifluoroacetic acid is even lower. Okay, the electron donating groups work the other way, but the effect's really not that dramatic. If we take all of the hydrogens of acetic acid and replace them with methyl groups, the pKa increases to 5.03, so it becomes a little bit less acidic, but the effect's not dramatic. All right, benzoic acid is an important one because we're going to, in the next slide, start putting electron withdrawing groups on our benzene ring, and so we're going to use that as a way to also look at acidity, or how electron withdrawing, or get a good measure of how electron withdrawing groups affect acidity as well. All right, so the reason that electron withdrawing groups are enhancing acidity is because of what they do to this equation right here. This is the Bronsted equation, and electron withdrawing groups tend to stabilize the carboxylate anion, which is the conjugate base of a carboxylic acid. And as this gets more and more stable, the reaction is more and more likely to go to the right. For most of these, the reaction goes to the left predominantly, but for the like trifluoroacetic acid, it actually goes to the right. Okay. All right, so recall that benzoic acid itself had a pK of 4.2. When we put the most electron withdrawing group we know, the nitro group, ortho to a benzoic acid, the pKa decreases, i.e. it becomes more acidic. It's not quite as acidic if you put the electron withdrawing group in the meta position, but in the para position, it's the compound's a little bit more acidic than it is in the meta position. This is because, remember, that the electron withdrawing or donating properties are most solidly felt at the ortho and para positions. Okay, so the weakest effect is from putting it at the meta position, and the para is a little bit stronger of an effect, even though it's further away. All right, let's look at dicarboxylic acids. We'll come back and look at them a little bit more in detail. But recall from the electrophilic aromatic substitution chapter that the COH is an electron withdrawing group. So we can think of this compound as just being a carboxylic acid with an electron withdrawing group directly attached, and it's quite acidic. Okay, this compound here is called oxalic acid, and it's a dicarboxylic acid. Note that it has two pKa's. Okay, so pKa1 is measuring this equilibrium, and pKa2, which is a much higher number, is measuring this equilibrium right here. All right. Okay. All right, so we're just going to compare the pKa1s for now. All right, so we as we move it a little bit further down the chain, this one, I'll just give you the name. There's common names. They're not systematic. This is malonic acid. What we see here is as the COH group has moved a little bit further down the chain, it's now the groups are now separated by a CH2 group. The compound isn't quite as acidic as it is over here. Okay. All right. So this is more acidic. This is less acidic. Now we're going to put two CH2 groups between them, and we see that the acidity is even less. It's still more acidic than acetic acid, however, so this effect is being felt. It's not until you separate them by about 4 or 5 that you see that the effect of the other carboxylic acid has kind of just disappeared. All right, so let's do an acidity ranking question here. Rank these compounds as to their relative acidity. This has a lot of carboxylic acids plus some groups from the past. Okay, what you should do is try this yourself and then restart the video. All right, some overriding concerns here are that we know that carboxylic acids in general are more acidic than thiols, which are more acidic than alcohols. All right, so knowing that, we can put this as number 6, and this is number 5. Okay. All right, we know that electron withdrawing groups are going to increase the acidity, and we already looked at this as being actually a really strong acid, so we're going to put that one as number 1. This one has no EWGs. This one has 1 electron withdrawing group, in addition to the carboxylic acid, and this one has 2 electron withdrawing groups in addition to the carboxylic acid. All right, so we're going to put this one as number 2, number 3, and number 4. And there's our ranking right there. Okay, so we're just looking at how many electron withdrawing groups do we have on the benzene ring, enhancing the acidity, and that's how we determine the relative acidity right there. All right. Okay, let's look at some acidity and solubility and equilibrium here. Okay, an important equation. It's kind of simplified, but it'll get you to a key realization very quickly, is this equation here called the Henderson-Hasselbalch equation. All right, so what it tells us, this is the equation right here. The pKa is equal to the pH minus the log of A minus over HA. What I'm going to do is rearrange it algebraically so that we're kind of focused on this value right here. What is the ratio of the anion to, or what is the ratio of the conjugate base to the free acid? All right, and we can subtract the pH from the pKa. All right, what does this tell us? If the pH equals the pKa, then this term right there is 0. And this means that the log of 1 is 0. Okay, so this means that we have a total 1-to-1 ratio of conjugate base and free acid when the pH of our solution equals the pKa. All right, if the pH is less than if pH is greater than the pKa, this is a positive number, and this means that there's more of the conjugate base than there is of the acid. Okay, and if the pH is less than the pKa, this means this is a negative number, and that means that the bottom of the fraction here is the larger number. Okay, all right. So that tells us what species is present. An important point to remember here, let's just look at the a few factoids about the carboxylate anion, or the conjugate base. Okay, this bond right here, the oxygen-sodium bond, is an ionic bond. So what we have here is a very high boiling compound. The conjugate base is typically exhibit salt-like behavior. So its boiling point is extremely high, up there with sodium chloride, okay? And it tends to be far more water soluble than the free acid. But I'm going to qualify that with a statement here. Okay, if people are asking you about the water solubility of carboxylic acids, you better pay close attention to how they're asking the question or how they're describing the water that they're dissolving it in. Okay, if it's just plain old distilled water, what happens here is that each drop of acid that you add to that distilled water drops the pH, and it's always going to exist as the free acid, and the water solubility will be much less. Okay, if you take this distilled water and you add the conjugate base, the opposite is going to happen. The pH is going to increase, and you're going to find that no matter how much of this you add, you're always adding the salt. So when you're dissolving these in distilled water, it's going to look like the conjugate base is a lot more soluble than the free acid. Okay, all right. Now, another type of water they might want to add this to is a buffer solution. So if the buffer is buffered to a pH that's above the pKa value, as most buffer solutions are, then what you're going to find is that the carboxylic acid and the sodium salt or the carboxylate anion have similar solubilities in that buffer solution, as long as you don't add so much that you've overwhelmed the capacity of the buffer. Okay, when we look at carboxylate salts that have really long carbon chains, we refer to these as being soaps. And when these dissolve in water, they actually organize into a very ordered fashion into the structure that you see over to the right. And we call this type of structure a micelle. What you find here is that on the outside of this micelle, you have the carboxylate anion groups, which are very hydrophilic, and they want to go out there and interact with the water through hydrogen bonding. But the long chain tails have no desire to interact with water, so what they do is they congregate amongst themselves, form these micellar structures, and this is what gives soap one of its special properties. Okay, so one of the best vivid descriptions is in a commercial for Dawn dishwashing detergent. So Dawn takes grease out of your way. So it takes it out of your way and puts it into the nonpolar region of the micelle. So what happens here, the reason soap works the way it does is it turns plain old water into a substance that can, to some extent, dissolve relatively nonpolar things, okay? And this is what's responsible for soap being such an effective cleaning agent, is that it has many more things can go into solution. All right. Okay, let's do a problem here. This is related to the Henderson-Hasselbalch equation. The question here merely is, what is the major species when each of these acids is dissolved in solutions at various pHs? Okay, and the Henderson-Hasselbalch equation is going to be our overriding concern. If the pH is less than the pKa, we're going to write the free acid. If the pH is higher than the pKa, we're going to write the conjugate base as the major species. So acetic acid at pH 2 is acetic acid. At pH 5, that's a little bit above the pKa, not much above, but we're going to see a slightly more of the acetate anion than the free acid. At pH 9, we're not going to see really any of the free acid, and we're going to see essentially all acetate anion. Okay, malonic acid here has 2 pKa's. 2.8 and 5.7. And remember from our explanation there, the first pKa is for converting the neutral compound to the monocarboxylate salt, and the second pKa is for converting the monocarboxylate salt into the dicarboxylate, okay, or the monoanion into the dianion. At pH 2, that's below 2.8, so we're going to see malonic acid. At pH 5, that's intermediate here, we're going to see the monoanion, and at pH 9, that's well above 5.7, we're going to see the dianion. Okay, trichloroacetic acid has a pK of 0.8. All of these pH values are above 0.8, so no matter what pH we have of these three choices, every one of them is going, for each of these solutions, the carboxylate anion is going to be the predominant species. Okay, thiophenol has a pKa much higher than acids, so at pH 2 it's going to be the acid. Even at pH 5 it's still going to be the acid. It's not until we get above 7 that we're going to see the anion as the major species. Okay, we're going to come back to problems like this much later in the class when we talk about proteins and amino acids. So just remember the Henderson-Hasselbalch equation. It's very important for determining what species of proteins we're going to have at a future area of study. All right, in this slide we're just going to look at some dicarboxylic acids in general. What we find here is that we'll first look at succinic acid, okay? So its pKa is a little bit less than acetic acid, and this we explained earlier that it's the electron withdrawing effect of the other carboxylic acid group enhancing the acidity. All right, so notice that pKa number 2 is a little bit higher than acetic acid. This is because you have two anions a little bit too close to each other, and that's a destabilizing situation. All right, so if we go from succinic acid, which just has 2 carbons separating it, to adipic acid, which has 4 carbons separating it, what we see here is a pKa number 1 a little bit closer to acetic acid. It's 4.41, and we see that the pKa number 2 is actually coming down because the two anions are a little bit further apart. And if they get really, really far apart, of course the pKa number 1 and number 2 are going to be extremely close to each other. A very important carboxylic acid is this one right here called carbonic acid, and this is very important in biological systems. This is how biological systems maintain their pH, is through a carbonate buffer. All right, so when we take CO2, carbon dioxide, and dissolve it in water, we set up an equilibrium between the gas and water and carbonic acid. This equilibrium, of course, you can buy it. This is when you buy it in the grocery store, it's called club soda. Okay, all right. So, and that's just a CO2 dissolved in water. All right, so the equilibrium here favors the CO2 in water, and when you shake up the soda can or whatever, what you do is a slight perturbation of this equilibrium that makes a little bit more CO2 and pressurizes it, and you can give it to your buddy and let them saturate themselves with Mountain Dew or whatever when they open their soda can. All right. Okay, so because this is the minor species at equilibrium, its concentration is already lower to begin with, and we see a little bit lower of a pKa value. This is 6.3 for pKa number 1. Okay, and for pKa number 2, it's 10.3. All right, so deprotonating carbonic acid once, of course, gives you bicarbonate anion, and that's a very weak base, right? And deprotonating it twice gives you carbonate dianion, which is actually quite basic. Okay, not as basic as sodium hydroxide, but clearly more basic than bicarbonate. Okay, and this equilibrium constant, I guess I have it here. As you can see from this number here at the bottom, the equilibrium heavily favors the CO2 and water. And this is, of course, why water becomes more acidic when you dissolve carbon dioxide in it. Okay, so this is where we're going to end this video, and then in the next ones we're going to look at synthesis and reactions of carboxylic acids.